Hello, welcome everyone. My name is Maciej K J. I'm the principal scientist at Haiku. And today I wanted to tell you just a little bit about the difficulty of running quantum algorithms on the actual quantum hardware, and also how Haiku is developing software tools to make this possible. One of these tools you'll be able to preview and hopefully also even deploy during the hackathon. So Haiku is a quantum computing software startup focused specifically on development of quantum middleware to help unlocking the potential and the practical utility of quantum computing in various applications, such as in pharma, logistics, finance, and many others. The promise of such applications is, of course, the main driver of any investment in quantum computing. So in this short presentation, I will cover the importance of quantum middleware in the quantum computing stack, and I will showcase some of the improvements in quantum circuit execution on near-term devices, which may be achieved using Haiku's technology. We'll also preview Rivet, the quantum machine learning tailored quantum compiler from Haiku. And finally, I will very briefly introduce the team behind Haiku, and I will mention some collaboration and internship opportunities for those of you who may be interested. So the roadblocks to the practical utility of quantum computing are in fact twofold. The first and the most fundamental one is the noise. Quantum hardware suffers from numerous sources of noise, all of which ultimately manifest themselves as errors in the final computation. So the rundown includes energy relaxation processes of T1 noise, dephasing, or T2, various coherent errors, such as, for instance, systematic gate over or under rotations, more complex correlated errors, such as crosstalk, as well as errors both in the initial state preparation and also in the final result measurement readout. All of these, if left unchecked, will conspire to render most any computation effectively useless, garbage noise. The other roadblock has to do with the limited scale of the currently available devices. The most obvious number to think about is the physical qubit count, but equally important is the device connectivity, its gate set, and the measurement rate. So different architectures may vary in these respects by orders of magnitude, and actually a fair comparison between them is not entirely trivial. While the focus is often on the qubit count, it is really important to note that the number of physical qubits has in fact been growing much faster than the effective number of practically usable qubits as measured, for example, by the quantum volume metric. As you see in the table on the right, some of the quantum devices with physical qubit counts in hundreds have rather small effective qubit numbers. That's the logarithm of the quantum volume metric. So what is this quantum volume? Well, quantum volume is a holistic measure of performance of the full quantum computing system, crucially including both its hardware and software components. On a more technical level, the test is statistical, measuring whether the likely measurement outcomes as defined by the idealized circuit you actually want to run are in fact still likely to be obtained when performed on the actual QPU system. And so the largest square-shaped random quantum circuit, which can be performed on the QPU and passes this test, defines the quantum volume of the device. In other words, it tells you how many high-quality controllable qubits on which you can perform operations and execute gates you really have effectively. And as you see from the table, that number is almost always an order of magnitude lower than the physical qubit count. Note also that the quantum volume test circuits are defined using idealized gate sets and linear topology. Therefore, before the execution, they have to be transpiled to the actual device gate set and the actual topology, and the properties of the architecture, such as qubit connectivity, as well as the quality of the compiling and other software involved in this compiling and execution process, will crucially influence the outcome. So there are, in fact, a number of different ways in which the quantum volume can be improved by software rather than hardware-based methods. The compilation process is an obvious one, as better transpiling will result in shorter depth device executable circuits, which are therefore less affected by the noise. Similarly, qubit mapping and routing may be also crucially important because it allows you to take advantage of the best possible subset of the physical qubits, which very often differ in quality, especially, for example, for superconducting architectures. So a key component in some of the impressive recent results on near-term device utility, such as the IBM's Quantum Volume 64 demonstration paper or the many body localization paper, has been also the use of software-based quantum error mitigation techniques, such as zero-noise extrapolation or probabilistic error cancellation. But in fact, there are many others available, and they come at a different computational cost. And so the development of such software components is the province of the so-called quantum middleware. So at the most basic level, we tend to think of quantum computing technology stack focusing either on its top part, that is the theoretical algorithm primitives, Grover's algorithm, Shor's, QFT, and so forth, and also their applications to the specific domains, the user-defined problems. Or on the contrary, we focus on the very lowest hardware level, that is the actual QPU and its control software and control electronics. Quantum middleware is the slightly less glamorous, but nevertheless entirely crucial intermediate component linking these two parts together, and thus, in fact, enabling any potential future commercial utility of quantum computing. Now, the two fundamental ways in which this software layer of quantum middleware can improve the performance of the whole quantum computing stack are through, one, reducing the impact of the hardware noise, to which I already alluded before, and two, through increasing the effective scale of possible quantum computations. That also includes the classical component. So many of the current demonstrations in the scientific literature are focused on small research level problems of purely scientific interest. In deployment to future practical applications, the computing infrastructure will have to contend with similar problems as, for example, providers of cloud-based computing resources for classical machine learning have to contend with today. So developing appropriate scalable solutions is also the province of quantum middleware. So with this in mind, Haiku focuses its efforts on the development of the quantum middleware as the key enabler of practical utility of quantum devices. The Haiku system comprises a set of components focused individually on each aspect of the quantum computing workflow from the perspective of the user, and is designed to streamline it. So first, the analysis tools to provide the user with the information about the properties of their circuits, particularly with respect to the intended hardware on which they are to be run. So this allows the user to anticipate the potential difficulty, achievable quality, and also to estimate the currently, unfortunately, very substantial dollar cost of the actual execution on hardware. Then there is custom compilation packages allowing flexible use of our in-house, third-party, and also open source components to tailor the best possible circuit for the actual execution. There is the error mitigation, which is a suite of our custom and also open source error mitigation methods, such as, for example, the already mentioned zero-noise extrapolation and a bunch of others. Finally, there is the circuit execution component. Haiku has proprietary strategies of executing the compiled circuit to minimize the impact of the hardware noise, and therefore to maximize the capabilities of the existing devices such as they are today. So let me now focus specifically on the optimized execution subsystem and showcase some of its capabilities. So to benchmark this component, we performed noisy simulations on fake devices of different vendors, both of IBM and others. So here I'm showing you the results of the quantum volume test that I already discussed before. So it's a quantum volume test execution on a simulated 27-qubit device, IBM 27-qubit IBM Kolkata device, which is available in Qiskit as fake Kolkata, for which, as a baseline using standard best Qiskit level 3 compiler settings, we measure the quantum volume of 32, that is 2 to the 5. That is, this device is able to accurately execute a random circuit of up to 5 qubit width and 5 layers depth. So this quantum volume result is consistent with independent estimates that are available in literature, and this is basically the level which is achievable by a typical advanced user. So the quantum volume is depicted in the plot, where on the x-axis we have the circuit depth, and on the y circuit width. And the area where the quantum volume statistical test is passed is denoted by the pale blue shading. As you see, with Haiku's optimized execution subsystem, the quantum volume statistical test is passed by the very same simulated devices in a much larger area, corresponding to the quantum volume of 128, that is 2 to the 7, and that's shown here in the darker blue. And I want to emphasize here that the gain is, of course, with respect to that chosen baseline, and that in principle, our tools can also be combined with additional optimization to provide even further increase in quantum volume. Well, this increase in quantum volume obviously automatically entails the ability to execute basically slightly wider circuit and slightly deeper too. But crucially, as you see in the plot, when we relax the constraint of running only square-shaped circuits, as in the quantum volume test definition, we observe that our execution strategy allows to accurately execute significantly deeper circuit than the nominal quantum volume value might suggest for the same circuit width, which, of course, that ability to run much longer circuits is very important in practice. Now, quantum volume circuits are a great test of devices and of the software system, but precisely because they're designed as a challenging benchmark, their complexity is actually beyond typical sparse application-derived circuit. And as an application-oriented developer or a practical user, you may therefore be interested in the empirical performance of the system on actual use case-derived circuits. So we have therefore performed a number of such benchmarks for different algorithm families to test well the optimized execution strategy. So here I'm showing to you the results of running so-called volumetric tests on a key algorithmic subroutine of amplitude estimation. So the results are plotted similarly to the quantum volume results from the slide before. And in fact, the quantum volume, both of the original and Haiku improved one are shown also. On top of that, we overlaid the fidelity of execution of amplitude estimation circuit with an increasing number of qubits. And as you see from the bottom plot, for the original execution, the 5-qubit amplitude estimation circuit, which lies already outside the quantum volume rectangle, so the circuit is already deeper than 5 layers. It has a fidelity of below 40%, and above that, above more than 5 qubits, the result is essentially noise. In contrast, with Haiku's optimized execution, 5 and 6 qubits amplitude estimation circuits are executed with high fidelity, despite being well outside the quantum volume ranges, and that only drops to 40% for 7 qubits. And we, of course, have similar results for other important application algorithm families. Now, I've shown you some of the Haiku technology and how it can improve the quality of the results obtained on the noisy processors. Obviously, there's a lot of research that's going into developing these techniques, but in tackling the more fundamental problems, we also continuously run into more practical daily challenges. And to overcome these, Haiku is developing some in-house solutions and utility software tools. And we've realized that some of these may also be of use to the broader community. And we have therefore decided to make some of them also publicly available. And one of such tools, the first one actually, that we release is an open source quantum machine learning compiler, which we call Rivet. And Yuriy P, our fantastic lead software engineer, will give you a preview of that. I'll shortly give the floor to Yuriy, but I'll come back at the end of the presentation. Yuriy, the floor is yours.
Thank you, Maciej. Hi, everyone. I'm Yuriy, lead engineer at Haiku, and today I'm delighted to talk about transpilation and how you could speed it up by a few order of magnitudes. I'm coming from AI background and work mostly on computer vision and reinforcement learning and building software infrastructure around them. So from my experience in AI, I have seen how good software tools like PyTorch and TensorFlow is important to build a community. And I feel the same for quantum, as AI in applications and AI in quantum pipelines, as well as software, is important to move a field forward. So as I joined Haiku about a year ago, and coming from different domain, I was onboarding to quantum. And one of my first tasks was to play with and understand how classical shadow works. Just to onboard everyone else, what the goal of classical shadow is to reconstruct a quantum state of your system. So how you could do it? First, you need to have a quantum system you want to measure. Then you could apply, you need to apply random unitary to change the basis of your system. And then you want to measure in this basis. And you just need to do a few thousands of this measurement to get the result. Then you could follow the protocol of classical shadow to do to make a reconstruction. And in the end, you will have your final reconstructed state. So don't be afraid. We're not going to dive more deeper into this protocol. It will just be example that we will follow through our slides. So let's just focus on how you could implement applying this random unity to a quantum system, and then doing measurements in some quantum framework like Qiskit. So at first step, we need to create a quantum state. You could easily do this using the Qiskit quantum circuit, and you just add some random gates that you want for our test case. Then you decide on a random Pauli basis you want to measure in, and just iterate through all of your qubits and add corresponding gates on top, and measure the qubits that you need. Then, if you want to run the circuit on a real hardware, and not only on some noiseless simulator, you need to transpile it. And I will talk more about this a bit later. But when you already have a transpiled circuit, you could run it on hardware and have the result. And remember, we need to do many more of this transpilation different bases and running to have the final result. I implemented this procedure on my machine, and it worked very slowly. So being engineered hard, I got annoyed and decided to debug how to solve this problem and tried to benchmark different parts of system. So what I found out is actually transpilation time taking so much. Just like look on the plot, and here you could see the total transpilation time for different qubit cases. And for example, for 8 qubit, you need to have a few thousand of circuit executions, meaning a few thousand of circuit transpilations. And considering a transpilation could be 1 or 2 seconds, it's a few hours of just transpiling a circuit, and not only including the actually running the circuit on the hardware. So that's clearly not the quantum future we all expect. So it got me thinking how we could solve that problem. So let's just take a look at our circuit. We have our state preparation circuit, which was very shallow, just with few gates. And also we have our random unitary circuit added on top, and this also was very shallow. But in practice, that's not the case. Usually the state preparation circuit is very huge, consisted of a few thousands of gates. And this random unitary is as small as I showed in example. So it got me an idea. Why not just to transpile the circuit before and then add measurements in the end? So how it will look like? We will have the same state preparation as before. Then we do a transpilation of this big state preparation circuit only once before our procedure. We cache this result. And then for each of our measurements that we want to add on top, we select, as before, a random basis, go through our qubits, add the gates on top of our already transpiled circuit, and measure the qubits. And then we expect it to run on hardware. So what's the idea? Now, because we are not transpiling circuit for each of the random unitary and doing it only once, we should save a lot of time. But sorry to disappoint you, this will not work. And to understand why it will not work, we need to know more about transpilation. So what's the goal of transpilation? On one side, you have a high-level circuit which consists of complex operations, like a QFT, multi-qubit gates, or even some random unitaries applied to a circuit. And on the other hand, you have a complex quantum hardware. And maybe not all of the gates are supported on this hardware. Maybe it has specific topology and not all the qubits are connected. Or you're not aware of the noise level of different qubits, and you need to really know to be able to run on the hardware. And so transpilers try to solve this problem. It converts this high-level circuit that you have to a low-level circuit that could run on hardware. It does so by unrolling these high-level operations to the gates that support on the device, by adding conditional swap gates, which allow you to connect qubits that are not connected in a topology, and additionally do optimization to decrease the number of gates of your circuit to make it smaller and so accumulate less noise. And now, as we know more about transpilation, we may understand why our naive approach of solving our problem didn't work. First of all, you cannot just add any gate to your circuit, expect it to work on the hardware. Maybe this gate is not supported on the device. Also, because transpiler adds swap gates, the qubits are located in different places on your physical qubits. And you really should know at what qubits you should put your measurements and add your gates. And also, this is not actually very case for our application, just because we are adding only single qubit gates. But when you want, in general case, add multi-qubit gates, you should also be aware of a topology of a device. So it didn't solve our problem. And why there is no simple solution for our problem? I think it's because the current transpilation procedure following a philosophy of transpile and forget, meaning that user has his high-level circuit that he wants to run on hardware, and for this he will use some quantum library like PennyLane or Qiskit. And as we already know, to run a circuit on hardware, you have to do a transpilation step. But usually in these frameworks, this transpilation step is omitted or hidden from user, and he could be not even aware that it's happening. On the other case, as I showed in an example right now, for classical shadow, a user should be clearly aware of transpilation and follow the philosophy of like transpile and reiterate, meaning when user has his original quantum circuit, he may want to transpile it once, then add some additional gates that he needs, transpile it second times, add maybe noise mitigation, transpile it finally, and only in the end run it on hardware. And in this case, transpilation is clearly visible for a user, and user reiterates on iteration results and adds his own things. So we see that this is not only the problem for classical shadow, but for many more applications, like in quantum algorithms, when you want to combine different subroutines, for example, QFT or Grover steps, or you want to do tomography. Also, it's very big problem in quantum machine learning. Just imagine you want to do layer-wise training, and if you're familiar from AI domain, you may want to understand how much layers do you need for your virtual circuit. And for this, you need to combine and stitch layers. And this is exactly the problem that we have with classical shadow, but actually much more complicated because variational layers actually have 2-qubit gates. Also, you may want to have a modular quantum neural network, which consists of different parts, and when you combine in runtime. Also, you may want to have a different data encoding that go to the same variational model, and you want to switch it very fast in your execution. Also, that's the case of noise mitigation. For example, probabilistic error canceling, a dynamical decoupling. When you apply them, you add additional gates, and you really want to make sure these gates are not optimized out from a transpiler. And if you also know some other problems, feel free to contact us, and we would like to talk about them. So as we at Haiku have been solving these problems, we develop our own internal transpiler, and we think it will be useful for the community. And we are happy to announce that we are releasing our open source transpiler called Rivet. And his main motto is get bigger control over transpilation. So what's Rivet? Rivet is open source transpiler which provides Qiskit-like API for transpilation and builds on top other open source transpiler. And the whole idea is to give user a modular approach to build his transpilation. So let's just go over some of its APIs to learn more about. First set of APIs that Rivet support is location API. We want to give user ability to control which part of circuit he wants to transpile and when. For this, we have a transpile right, transpile left API, and other functions. Why would you want to use them? Let's just come back to our previous example of classical shadow. We have a circuit that consists of 2 parts. One of them is a big state preparation circuit, and one other is a random unitary that we want to add on top. And that's exactly case for location APIs. Do we really want to control location of the circuits we want to transpile? Now, let's see example how we could use transpile right to solve our previous problem with classical shadow. First, we have the same state preparation as we was before. Then we do transpile a big state preparation circuit once, as we did in our naive approach. Then what's different, we create a separate measurement circuit consisted of our random Pauli basis and add gates as we want. Then we use this new function called transpile right. And transpile right has 2 arguments. One argument is transpile circuit that you have on your left part. And then on next argument is not transpile circuit that you have on the right. Now you could use this function, and it will return you merge these 2 circuits that are valid and transpiled, and you could run on hardware. Why this is very important? Because in this case, we are only transpiling these very small unitaries, random unitaries that we added on top, and not transpile our whole circuit. Now, as we have the saving, we could run benchmark one more time, and we see that our basic transpilation took so long, and we decrease a time from a few hours to just a few seconds, just only doing the transpilation. So let's just move to our debug API. So as our motto of a transpiler was to give user bigger control over transpilation, user should be aware of transpilation at first place. So for this, we have a transpile and debug function. It will not only transpile the circuit, but also return you list of all detailed information of transpilation, like what's transpilation passes, how much time does it take, and how did it change your circuit in terms of used qubits and used gate. Now you could make more informed decision about your transpilation. The other set of APIs is related to constraint API. And we want user to be able to control different properties of transpilation and prioritize some of them over the others. For this, you could use a transpile and compress function, which I will talk a bit right now. And why would you want to do this? Imagine a case when you have a 9-qubit circuit, and you want to run it on some hardware or on some noisy simulator. First, you need to transpile it. And what could happen is that during the transpilation, your transpiler adds additional ancilla qubits. Why would transpiler do this? Maybe he will want to decrease the depth of his circuit, and he uses just additional qubits to bridge the gap of connectivity in your circuit. This is cool. It saves you depth, but you pay the price of additional qubits. And you may really don't want to have them. Why? You may know that on this hardware, using the ancilla qubits is actually not welcomed. Or if you want to run your circuit on noisy dense matrix simulator, it's really important to control how much qubits you really have in your circuit. So let's just see the benchmark of running 9-qubit and 10-qubit circuit on noisy simulator. So 9-qubit circuit will take, for example, a few seconds to run. But 10-qubit circuit on some noisy density matrix simulator could take more than 10 seconds to run. And just imagine you want to run a QML job, which consists of 1,000 evaluations. So on 9-qubit circuit, and just running will take 25 minutes, but when 10-qubit circuit, it will be 200 minutes. So that's why important to say the transpiler how much ancilla qubits and additional qubits you want to use, and that's exactly a function of transpile and compress. Now we could move to the last set of our APIs. It's called modify API, and we want to give you the ability to not only constraint API, but also change different parts of API and replace with others that you want. For this, you could use our stacks. So right now we have this available stacks. It's other open source transpiler like Qiskit, PyTicket, BQSKit with QFactor and QSearch. And we want user to give more power to use the best features of this transpiler. So why would you need to do this? Imagine you have your quantum circuit, and this circuit consists of two parts. One part is some sparse in terms of gate circuit, and other part is very dense circuit. And you may know that, for example, for this sparse circuit, synthesis optimization will do the best. Sorry if you don't know what is it, but it's kind of one of the ways to optimize your circuit. So, and you may want to use a Q factor to do this optimization. But how would you do it normally? You just have to run the synthesis optimization on your whole circuit. But you know that this big part is actually much harder, and there is no point to make running synthesis on it. So now, with combining location API and combining our stacks API, you could solve this problem. You just split the circuit in two parts, and you transpile this dense part with default transpiler, which works pretty fast. And then you transpile the other part with synthesis optimization, and it has a good quality result. And then using our location API, you can combine them together. So what you will have in the end, you will have better performance and shorter circuit, and also you will save time on transpilation. So let's just wrap up what we go through. First is that transpilation is a very important step in your quantum pipeline. Second is that future application will require more complex transpilation strategies. And we show that Rivet has bigger control over transpilation, and also it will enable this future application and optimize performance. So we are happy to open source our transpiler, and we know that hackathon is happening right now. And if you feel that some of the problems that you face could be solved with Rivet, I encourage you to go to our GitHub and go to the examples. They are in more detail, describe the API and how it works. And also, if you have some questions, please ping us on Discord, open the issue on GitHub, and contact us on email or me on LinkedIn. And also, if you're coming from industry and facing the same problem as we do and want to collaborate, we are very happy to work together. And also, please contact us on our emails. So thank you all. I will pass my word and stage to Maciej.
Yeah, thanks a lot, Yuri. So yeah, as we have shown you, Haiku is focused on the fundamentals of quantum circuit execution, but we're also actively developing both methods and software toolboxes to aid various practical problems that we encounter. So we are therefore extremely happy to be able to be here at QHack and to interact with the vibrant community of quantum software enthusiasts gathered here in Toronto. And even more so as Haiku has in fact originated in Toronto, where the two founders, Richard Givan and Mikko Maximenko, met in the Creative Destruction Lab incubator. Now, over the span of a short year, Haiku has grown from the founding team to a globally distributed team of almost 20 researchers and software engineers. We have a strong presence in both North America and the EU and UK. We are always happy to work with dedicated developers and also researchers. And we have a research internship program to which I encourage you to apply. So you can find the details and the contacts under the links provided in the final slide. And with that, I thank you for your attention, and I wish you a successful and most importantly, exciting hackathon. And that's it. Thank you very much.
All right, Maciej and Yuri, thank you so much. I'll leave this slide up for a bit in case people want to go to Haiku's website and see anything else here. Thanks so much. That was really interesting. Had some good questions in the chat, so we might as well just get right to those. We have Gloku42 on our Twitch channel asking, I think earlier in your presentation, Maciej, you were showing some results and they were wondering if there's a paper that you guys published with any results.
No, so the results are not available in the form of a paper or an ICA publication. Okay. We are happy to share the results in the form of a white paper with interested parties. But I have to be fairly honest here that we're currently keeping it to sort of collaborations with potential partners. So we're not disclosing the further details in the form of publication. But of course, one will be forthcoming.
Sure. Okay. Thank you. Another question from Dentucky Kirby on our Twitch. I always get confused. What's the difference between transpilation and compilation?
I could
please go. Please go.
It's very technical one, but basically, what compiler does, it usually converts your code from the high-level language to the low-level language. For example, like in C++ will be converted to assembler. But transpilation is much different. It actually converts maybe the code from one level and to the same level of abstractions. And you shouldn't be thinking that transpilation is much more easier. Usually, compiling to a low-level language is simpler.
Okay, there you go. That's the quick answer there. All right, I had a question actually. So I put it in the chat, but I'll just read it off here. So Haiku's partnered with the Perimeter Institute, mostly like Roger Melko's Pickle branch of Perimeter. That was announced recently. I can't remember if it was last year or early this year. But anyway, Roger was here last week to talk about open quantum design. And I can't remember in his presentation if he mentioned Haiku at all, but I'm wondering if Haiku has a role in what open quantum design is up to, and can you comment on that partnership?
Yes, so we are joining the open quantum design. But I think this is a fairly fresh subject, so I'm not sure if you already officially announced as the partner. So that's as much as I can tell you on this.
Oh, okay.
Unless Yura is able to share a little bit more details on this. Correct me if
we want to work on other open source initiative in part of this project.
I see.
Okay.
So the short answer is yes, we'll be actually joining, but this is in the working.
Cool. Interesting. All right. Right. Okay. There was a question from Gloku42 again about the GitHub repository. It's on the screen right now. I'll just put that up there on the presentation.
Oh, sorry.
Yeah, just about like where the.
I missed the slide.
It was the one you had up.
It was here. It was this one.
Yeah, it was that one. Cool. Yeah, that's where to go. Scan those QR codes right now. I'm gonna take them off the screen in 3, 2, 1. Okay, cool. We have another question on Twitch from Raftersaurus. For the middleware stack you guys are developing, how close to the hardware will you eventually need to run? Can all this happen on the user side, or will you need to do some collocated execution with quantum hardware?
Oh, that's actually a great question. So that's one of sort of the fundamental things that we're thinking about, and the way the system is set up currently, and you have to understand that we're of course a very young startup, so we're moving very fast, but there's only so much we can do. Is we're working on the higher level. So we're currently thinking of hosting most of the compute intensive things in the cloud. But of course, for future efficiency, one will have to move closer to the devices and also think of co-located solutions. So that's something that we're thinking about, but that is not part of what I've been advertising to you right now. But it's, of course, it's an important consideration. That's actually a perfect question.
Cool. All right. We just had another question come in from Entiedo too. Can you elaborate more on the example of the Stack API? I think you had a slide with like 4 different, that one. Go ahead.
So as you may know, a transpilation consists of different steps. Actually, there is a routing phase, layout phase, all different phases there. And with Stacks API, you could replace some of the phases there with the passes from different open source transpiler. And you may know that this transpiler works better on some of the features. And now you could build your own transpilation pipeline using these passes from different transpilers. And maybe you just simply, maybe in simple case, you may just want to transpile with different transpiler with one API, and you could want to test how it works. I think it's something that you could start with right now even.
Cool. I have one more question too. I asked this yesterday to Jinsung from NVIDIA. There's quite a bit of I think the theme this year of this Q-Hack is like compilation. Like that's the next big thing in quantum programming, I think. So would you guys say that if people are looking to get in quantum programming, is it more worth your time? Obviously do whatever you enjoy, right? But is it worth your time is it more worth your time, to like learn LLVM or something, or MLIR or something like that, instead of becoming a Python ninja now? Like what's your guys' take on that?
Well, I mean, I can tell you that LLVM that's really getting to like level hard maybe, but of course if you do that, then possibly we'll be able we'll be very happy to talk to you.
Right.
So actually it's probably a great idea for your employability, because that's actually a really hard skill. Like there are no, in general in quantum computing we have a bit of a problem of shortage of people with specialized skills. Traditionally, the source of pretty much everyone in this industry are actually university departments of condensed matter, both experiment and theory, and people involved in numerical methods. Maybe more recently also people coming from AI. But if you want to acquire such specialized skills, I think they're probably they will be in short supply, and you'll be very successful. But on a kind of like less hard level, I think this is actually a super cool area to get into, because on one hand it involves some very nice algorithmic and software engineering challenges. So I think it should appeal to people coming from this background. But on the other hand, if you look at various solutions available, for example, in the context of hermitication, I think they're also very interesting from the scientific point of view. So if you're coming from like a more academic, theoretical background of condensed matter physics, that's also very nice. And I would say it is probably more interesting thing and more practical thing to get into, the current industry and the current startups and so forth, than just learning to execute, let's say, Grover search in a kind of, idealized setting and trying to say that you're going to solve like some, finance problem.
Cool. All right. That was a good answer. Thank you for that. One more question from Guillermo in the chat here. You've shown several times topologies of IBM quantum computers. So from your experience, does this structure make sense to facilitate transpilation?
So we are, we obviously, looked at IBM because, IBM is pretty much the gold standard there is. And the topology is dictated by physics, right? It's a superconducting device. There are of course other devices being developed that are based on entirely different physical platforms, and they all have their other advantages. And it's a little bit of a question that I'm not sure if one can seriously answer like in full generality, because it's not like IBM actually has the choice to to do an all-to-all connectivity with their with their physical system, right? So I think it's a trade-off, and I will certainly not be as arrogant to claim that I would have chosen a better topology than the heavy hex that they've done. But of course, topology influences everything, but it is dictated by other constraints of your physical platform.
Right. Okay. Well, hopefully that answers your question, Guillermo. I think we'll leave it there. If you guys do want to learn more about Haiku, maybe you guys could show that slide again. Oh no, it's up already. Cool. With all the with your website, go check out our job, the QHack job board as well. There's a listing on there from Haiku.
Yes, and of course, if you are interested, please contact us. There are various channels that you can go via LinkedIn or via the website. And if you do actually check out the Rivet compiler, then we will be super happy if you provided some feedback. And if God forbid some bug appears, that's also super welcome. So enjoy.
Right. All right. Well, Maciej and Yuri, thank you so much. Looking forward to see what Haiku's up to in the next year. Maybe we'll be back next year at the next QHack to tell us about some more cool stuff.
We hope so too.
Yeah.
We hope so too.
All right.
Thank you.
Thank you so much. Have a great rest of your day and take care.